First of all, I would like to prove that Allan variance is something which is quite simple, very simple, not quite, very simple. And in order to prove that, we will use the simplest spreadsheet that we can imagine, which is called the numeric. And we will try to use, to launch numeric and to work to compute an Allan variance with numeric. Okay? So I will try to do the same thing at the same time with my computer. So we will see. This is we will begin with only a small command line, which is the launch of the spreadsheet. So I will launch numeric. And the file that we will try to see is this one, tuto-allan.ykt. Just one precision, every time that you see a suffix which is ykt, it means that it contains frequency deviation data. You remember that the frequency deviation are generally symbolized by the letter y. On the other hand, .xtt means that you have time error data. You know that the time error, if you want to retrieve the ykt, you will have to derive them. But anyway, we will see that later. What we will look at is tuto-allan.ykt, which is a very small list of data. You will see. So I will launch numeric like that. I put an ampersand in order to be able to launch other commands. Okay, so you should have the same thing as me. This is the content of the file tuto-allan.ykt. Here you have a first column which represents time tags. So it means 1 second, 2 seconds, 3 seconds, and so on. So it means that you have a sampling time which is 1 second. It's a simulation, it's not real data, but it's only to show you how it works. And here you have random data which symbolize what could be a time series of ykt, of frequency deviation. So do you remember the algorithm of the Allan variance? It's written here.
Yes.
So you have to do y2, so this one, minus y1, this one. You take the square and you divide by 2. So you just have to do that in this column. So we will try to do that right now. Okay, so you see that, I don't know if you are able to read what is written here. B2 minus B1, between parentheses, you take the square and you divide by 2. Okay? What we have to do now is to make the same for all the couple of the pair of the adjacent samples. So you have to do also B3 minus B2, B4 minus B2, B3, and so on. So in order to do that, you just have to use the cross which is here in the right bottom corner, and you go down, but you have to be careful because you can go more down than this, because here you have the difference between B10 and B9. If you go one step beyond, if you go one step beyond, it will not be possible because you have B11, and B11 doesn't exist. So don't do that. So we have now all the square difference of this data divided by 2. What is the result of the Allan variance is to take the average of all that, because you remember that in the relationship which is written here, the brackets mean that you are doing an average. So I will make average of all that, it's quite simple. You just have to write here equal average. You open the parenthesis and you go from here to there. And I got this first result. So what is this? This is the Allan variance with an argument tau, which is tau equal 1 second. Now what is very interesting is to make the same with tau equal 2 seconds. How is it possible to do that if you want that tau equal 2 seconds? You have to combine these two ones, and after that you will move a little bit on that. Make all the possible differences that we will make an Allan variance with overlapping. So
can we do like more than 2, for example, let's say 5 seconds?
Yes, after that we will do with 3, 4, 5. Okay, so first with tau equal 2 seconds. So here I will make first the average of this 2 one. B3, B4 here, minus the average of these 2 ones, B1, B2. I close the parenthesis, I take the square, and I divide by 2. Okay. And after that, I will do the same. I will go down in order to have all the possibilities. And I think here is the last that I can use. Okay. Okay. Computation. So the computation is the average of B3 to B4, which are there, minus the average of B1, B2. I take the square and I divide by 2. And after that, the second one, you'd shift of just 1 second, you shift below, and you have here B5 minus B4, average of B5 and B4, minus the average of B2 and B3. Okay? And after that, you do all the possibilities. We can do that in the order that you want, because since it's a square, you can make the average of B2, B3 minus average of B4, B5. It gives exactly the same result because it's a square. So it's the with overlapping, yes. If you don't want to make with overlapping, you have to suppress this one over 2 of them. You have to, but generally it's better to make overlapping because the statistics is better. You have more value to make the average. I did it for 1, for 2, I will do it for 3, and after that for 5. For 3 here, I will make the average of the 3 ones. I forgot to make an average, sorry. Average of B4 minus this is minus average of B1, B3. Okay. I take the square and I divide by 2. And here is the last that I can use. Okay. So now I will go directly to tau equal 5. If I do tau equal 5, you see that we have only 10 value. So it means that we will take these 5 ones, the average of these 5 ones minus the average of these 5 ones, and you have only 1 value. It's not necessary to make an average because you have only one value, but we will use it either. Quand même, equal average. Okay. What we can do now is to verify that if we launch in the window which is here, if we launch the command line which will compute the Allan deviation, which is called adev, tuto Allan.ykt, what does it mean? What does it give you? It gives you for tau equal 1, for tau equal 2, for tau equal 4. Ah, it's 4, it's not 3, sorry. Anyway, we will don't use this one. And tau equal 5, it gives the results. Are they compatible with what you obtain with the numeric? You think this is compatible with that? No. What's the problem?
It's a deviation and not a variance.
Exactly, it's a deviation. We compute the Allan variance here. And you see that here we have the Allan deviation. So we have to take the square root of that in order to have something which should be the same. We will try. Here I will, square root is SQRT of this case, okay, and I will do that for all of them. Okay. So now we have 8.74 10 to the minus 1, which means 0.874, 0.874, and so on. And the second one, you have 0.828, 0.828. And the last one, because this one is not the same, because it has been computed with 3, this one with 4. So the last one is 0.476, and you have 0.476. So it's overlapping, yeah.
So it doesn't make sense to compare with this.
This one is overlapping also.
This is also
yeah. Okay. In the general case, everybody make overlapping variance. It's when you have the algorithm, it's so easy to do an overlapping variance that we do an overlapping variance. The advantage is to have more statistics, so you have something which is a little bit the uncertainty bars around the Allan deviation value are smaller. So you have to do that. SigmaTheta-gui here, and if you launch it, you will have a window like that, and you can choose what you want by using or by clicking here. You will have the possibility to open a new file. So the first one that you have to open is the file which is named cshour.ykt. So what we want to do now is to look at the file which is called cshour.ykt. So we open this. You see the data, you type OK here, and you should have something like that. Everybody have something like that? So just one explanation about the name of the data. It's called CS hour. It means that it has been obtained with the cesium clock, and we have one time tag every hour. It's the reason of hour is because you have an integration time of each data, which is 1 hour. Okay, and so it means that you have several days of observation in this case. What we can do is to do directly the Allan deviation here. If you want to make the Allan deviation, you have to select, but it has been already selected by default. So by default, you have the Allan deviation. The integration time, you see that it's 3.6 10 to the plus 3, so it means effectively 3,600 seconds. So it's really 1 hour, and you can make run. If you make run, it will compute the Allan deviation. And if you display asymptotes here, you will have the asymptotes directly of your data. The question is, what are these asymptotes? You see that we have two main asymptotes, an horizontal one, which is green. There is an horizontal one and one which is like that. And there is a small one here, but we don't care of it because it's not significant. It's just at the end of the plot. But two mains are these two ones. But here you have an uncertainty domain, which are very small, and you see that it's very well fitted. You know that theoretically, if we want to look at the model is the sum of these two asymptotes. And if we make the sum of these two asymptotes, here it means that it's not here the position. It should be approximately here. So it's really well fitted by the asymptotes. Okay. If we have an asymptote which is horizontal, what does it mean? You have the table here which gives you the asymptotes in tau for all the different type of noise, which are the different type of noise which are on the left. There is one which is constant, I mean, which doesn't depend on tau. Which one? The second one, h minus 1, f to the minus 1. So it's the asymptote which is due to the 1 over f noise, the flicker frequency noise. So this is due to the flicker frequency noise. And this one, you see, it's you have to remember that it's Allan deviation which is plotted here. The Allan deviation is in 1 over square root of tau. So it means that if you take the Allan variance, it will be in 1 over tau. What is the asymptote which is in 1 over tau? White frequency noise. So it means that you have a mix of white frequency noise and of flicker frequency noise. Okay? And it's possible to go further because you see that, for instance, I take this one, or perhaps I will take this one, it's easier. You see that you have the Allan deviation, I will explain that here, sigma y of tau, which is equal to, which is constant and equal to, I will say approximately 9 10 to the minus 15. Okay. 10 to the minus 15. Okay? And you know that sigma square of tau is equal to 2 log of 2 h minus 1. The goal is to obtain the noise level, the flicker frequency noise level. What can I do? First, you see that you have something which is square here. First of all, you have to take square here. Okay? And after that, you make you have 2 log of 2 h minus 1, which is equal to 9 10 to the minus 15 square, so h minus 1 equal 9 10 to the minus 15 square divided by 2 log of 2. Okay. It's possible to have an idea directly of the result here. In order to do that, I like to use Octave. Octave, perhaps you know, it's a clone of MATLAB. So if I put here, I will call it h minus 1 equal 9 10 to the minus 15 to the square divided by 2 log of 2. Okay, and I obtain 6 10 to the minus 29. I drop all what is beyond the dot. It's 6 10 to the minus 29. So I have the noise level. I have an estimation of the noise level of the spectral density. We are doing spectral analysis in this case. Are you able to do the same thing with the other asymptote? You have another asymptote which is this one. This one you have the Allan deviation is let's say 8 10 to the minus 22 n to the minus 12, sorry, tau to the minus 1/2. What is the corresponding noise level? Equal 8 and you know that it's the asymptote of the wide frequency noise. So it's here, it's what? H0 over 2 tau. So I forgot something which is very important here, which is over tau. Yeah. And so it means that H0 equal, so H0 is equal 2 times this. And it's possible to do that without using Octave. It means, sorry, square. 64, 128. 10 to minus 32. It means 1.3 10 to the minus 30. Approximately. Okay? You agree? So it means that the spectral density may be modalized by equal. I take already first the h minus 1, so it means 6 10 to the minus 21 multiplied by 1 over f plus the white component, it means the constant component of the spectral density, 1.3 10 to the minus 30. How can we verify if it's true or not? We will compute the Power spectrum. There is a possibility to do that by using this button, which is
12, yeah.
yes, it was minus 12. Okay, you're right. Yes, I don't know why I put Okay, so it's not 16, it's 12. So it means that here it should be 24. And here it is 22. Okay, so what can we do? Perhaps I will use another panel. You can change the panel by using new here. So I will take this one, which is void, and I will open the same data file here. Okay, and I will directly here compute the spectral density, PSD. Okay, that's it. Do you think that what we observe here is compatible with this? First of all, there is a part which is approximately constant, which is 1.3 10 to the minus 22. I forgot to correct here. So you have 10 to the minus 22, which is here. It's a little bit above this value. It seems to be okay. The other one, we see that, for instance, if I want to make a fit here, I would say that you have here we have a 10 to the minus 8. Roughly, we are approximately at 10 to minus 20. If the frequency is 10 to the minus 8, the spectral density is roughly 10 to the minus 20. Okay, I will try to do that. If you have 6, 10 to the minus 29 divided by, I said it was 10 to the minus 8. I will obtain, you just have to do that. Yes, that's it. It means that you have 6, 10 to the minus 21. 6 to the minus 21. Minus 21, 10 to the minus 21 here, and 6, 3 should be there. 6 is almost here, so it seems to be quite compatible. Okay, so you are able with the Allan deviation to retrieve the noise level and to have an idea of the large trends of the spectral density. Okay. Okay, so it was the first exercise. Now we will. It's possible to do the same exercise with all the data, but we will focus on other things because we don't have time to do that. Now I will open a new panel, and I will get the file which is called hmminute.xtt, and it's look like that. Oh, sorry. Problem is I forgot to put in this. I do it again. hmminute.xtt. Okay, that's it. First of all, what we see is the fact that we have a file which is ended by xtt, so it means that there are time error and not frequency deviation. So first of all, you have to translate that into frequency deviation. So there is a button here, x to y, which will do the job. You have also to make sure that you know what is the integration time. The integration time, the sampling time in this case is 60 seconds. And it's, you remember that the name is minute. It means that you have one data every minute. So what we have to do is to translate this, and what will be done, it will be it will make the difference between two adjacent samples at each time in order to make the derivative and divide by 60. So I click on this button, x to y, which is here. It asks me the time tag factor. In this case, it's the time tag factor is the sampling time, so it's 60. So I put 60 here, and I obtain this. Okay? When I want to go from x, which are all the value, I know that yk is equal to x of t plus tau minus x of tk divided by tau. And in your case, what is the important value? Tau is equal to 60 seconds. So it will take all the adjacent samples, make the difference between them, and divide by 60 and on all the sequence. And you will obtain what you are able to plot now. Everybody has this curve. It was phase type data at the beginning, and now it's our frequency deviation data. Okay, so now I will try to make a Allan deviation of that. So I will launch, I put run here, and I look at the asymptotes. Okay. What can you see on this? What are the different asymptotes here? You have the first one, which is as previously, which is in 1 over. There is a small one which don't care because it's very low, which is in tau minus 1. Tau minus 1, what does it mean? Allan deviation in tau minus 1. It means the Allan variance is in tau minus 2. So what is it? What is this? White phase, or it's written also in your booklet. No, not random walk. It's white phase or flicker phase noise. Both are the same 1 over tau square. So we don't know, but we don't care because it's not visible. So we will see that with another example. The second one, the blue one, the blue on my screen is in 1 over square root of tau. So if you take the Allan variance, so take the square, it will be in 1 over tau. 1 over tau, we already saw that. It's directly due to the flicker frequency. So we have a part of flicker frequency which is sensitive for the short integration time. After that, we have white phase, white frequency noise. Sorry. After that, we have the flicker, which is the flow which is here. And after that, you have 2 more asymptotes. One is in square root of tau. So if you take in your table, it will be in tau. What is this?
This is random walk.
Random walks. And another one, which is in tau here, which will be in tau square, which is a drift. The drifts that you mentioned just before on the graph that you can retrieve if you look at preview is also measured here. What is the problem here? The problem is the drift. The drift is quite well measured here. You have several dots which measure the drift, but you see that the random walk, which is also important, and generally it's very important to estimate the level of the random walk, because for very long term it will be the most important noise, so you have really to know it. But here you don't know it very well because it's partially hidden by the asymptote of the drift. So what can we do if we want to see clearly, if we want to be able to measure the random walk?
So the drift, we remove it?
We remove the drift. We will try to do that. In order to do that, I recommend that you use another panel in order to keep this one, because we will compare If you do that in another panel, we will compare with this one. It will be easy to go back to this one. So I put a new panel here. I go inside this new panel. I open the same value, the same file, which is HM minutes here. Okay.
This one is the lowest one.
As previously, I go to the frequency deviation data. So I put the time tag factor, which is 60 seconds. I got this. And now, everybody has this. Now there is a button which is here. You see a small drift which is here. If you click on this button, you will remove the drift. So I click on this button. He asks if we want a drift of degree 1. Yes, we just want a linear drift. It's possible to remove quadratic and so on, but we only remove the degree 1. Okay, that's it. So here you see that you will no longer have a drift. You have an average which is approximately 0 and no drift. What is possible to see also, it's possible to see that what we measure here is 1.07 10 to the minus 20. This is the coefficient of the drift. If you consider that you have an equation which is given by that, y equal d1 multiplied by t, d1 here is equal to 1.10 to the minus combien? 20. Okay? What we can observe directly is if we go back to the panel, the previous panel, the previous panel told us that we have here an asymptote which is given by this value, 8.1 sigma, so not sigma square, which is 8.1 10 to the minus 21 2, sorry. And from what I see in the here, this is equal to square root, because it's a sigma here, of 1/2 d1 square tau square. So it means that it's d1 tau divided by square root of 2. So if I have d1 divided by square root of 2, it should be, is equal to 8.1 10 to the minus 21. So d1 should be equal square root of 2 multiplied by 8 10 to the minus 21. What give you, I will make the computation with the octave. Minus what? I don't remember. It's written here. 10 to the minus 21. And then obtain approximately 1.15 10 to the minus 20. Yeah. And I obtained previously this value. So it's not exactly the same, but it's not very far. Just one advice. If you have, yes, sorry, it's too, it's too low. I prefer to use this value. I think this value is much more accurate than this one because the Allan deviation is not exactly, it's not so precise, not so accurate if you want to measure the drift. But nevertheless, you have an estimation, a rough estimation of the drift by using the Allan deviation. Okay, so I go back to my other panel. I go back to the panel here, and now I will make the Allan deviation of this, and with asymptotes. Okay. What do you think of the asymptotes of the?
Now we can see the random walk. It's much better.
We can see the random walk, but we can see also that there is missing something. You see that the data.
Yeah.
How could you interpret this? I think that we remove the drift, but perhaps not only the drift. It seems that we remove also some behavior which are due to the random walk itself. Because if you have random walk is a very long-term noise. You can have, let's say, false drift which appear, and they are removed at the same time that there is a real drift. There is not possible to distinguish a real from a false drift. The term false drift or real drift is not very rigorous. So it will be removed. So it means that if you look at, with the Allan deviation, you have something which is going down here. So it's not a good solution to do that. What could be the best solution?
The Hadamard.
The Hadamard. And why the Hadamard?
He rejects the drift.
Because it's insensitive to drift. Yeah. So it means that whether there is a drift or not, it will give you the same result. So whether you remove or not the drift, it will give you the same result. So what we have to do is to go to another panel, because it will be possible to compare. We go to another panel and we will not remove the drift, sorry. We will use the Hadamard variance. So, okay. I use another panel. I load a new, the file name, which is, I don't remember the name, hm-minute.xtt. Okay. I still have to convert it into frequency deviation, so I still have to put the time tag factor, which is 60 seconds. Okay. And now I will change here. I will not use ADEV, but I will use HDEV, Hadamard deviation. And I put run, and I display asymptotes. And now you have something which is relatively clear. You have here still the 1 over f, the white frequency noise, the 1 over f which is here, and the random walk. And now you have, you see that these 2 points are very large uncertainties, so it's not clear, but you still have something which is interesting here. And now you can consider that you have a better estimation of the random walk.
What is the action?
Yes, this is this is directly the result of the Allan deviation computation, the one that you did. Okay, but after that, in order to get the uncertainty, I compute the PDF, the probability density function. You will try to explain that. It's an important point, of course. You're right. I forgot that with the group, but it's a very important point. So I will go back to the plot series here. these two dots here, you know that you have a very huge uncertainty domain. So it means that if I want to represent the probability density function of this measure, which is here, we should have something which could go from, this is a PDF, probability density function. You see that it goes from approximately 9, 8, 7, 6, 5, 4, 3, 2, 1, 10 to the minus 15, let's say 1.5, 10 to the minus 15. And the end is approximately at, I will take this one, 2, 3, 4, 5, 6. 6, 10 to the minus, 12, 14. So you have a curve like that. The probability is a little bit, it's not symmetrical, it's a chi-square distribution. So you have something like that. You have 2.5% here, 2.5% here, because the error bar are at 95%. Okay? So the probability of the true value is somewhere. The value which is directly the measure which is given here, you see that it's the measure is exactly at 2, 3, let's see it, 3, 10 to the minus 15. This is a measurement. And what you give as an unbiased value, it means this is the mean value that you can retrieve by knowing the probable density function. It's clear or not?
And how is this function calculated?
But we know that it's a chi-square distribution. So we know perfectly what is the PDF. So it's possible to know, if you know the PDF, what will be the average is given by table. And the average is given, the mean value is given here. You know that if you want to know the average, you have to do you have to make you use this relationship. Perhaps we go a little bit far in the statistics of the Allan deviation, but it's just to give you an idea of what is done. So you know that if you have the PDF, you are able to know the mean value, you are able to know the median. The median is the region where you have 50% to be low or 50% to be higher. It's also possible to go to the maximum of the PDF and so on. So there are many estimates that you can use. But you see that when you have an error bar which is so large, it's not very interesting to know what are the different estimates. You know that you have a very inaccurate estimation of the Allan deviation for this value, because you are really at the end, you have only one. So remember that each time that you make an Allan variance measurement, you have a distribution which is a chi-square distribution. The problem, which is not so obvious, is to know the number of degrees of freedom, because the only parameter which is of importance for a chi-square distribution is the number of degrees of freedom. You know, a chi-square distribution is nothing but the square of a Gaussian noise. If you have Gaussian value, you take the square of the Gaussian value, you have a chi-square distribution with 1 degree of freedom. If you have the sum of 2x plus y to the square, it's with 2 degrees of freedom, and so on. Okay? So we know perfectly what is the behavior, the statistical behavior of the estimates of the Allan variance. But we have to know what is the number of degrees of freedom. There is some algorithm to do that. but I will not go further in the detail because if you are interested, I can give you some clues, but I don't think that it's necessary today to go so far. Okay, it's clear for you. So we will go back now to another panel, and I will try to use the last file. The last file, which is this one. Okay. So this one also is the suffix is xtt, so it means that you have time error, you have phase time. So we have to translate that into frequency deviation. So we will use x to y as usual. You see that you have an integration time now, which is no longer 60 seconds, which is no longer a minute, but it is 1 millisecond. So we will have to give the time tag factor, which will be now not 60 but 0.001, 1 millisecond. Okay, for everybody? Okay, and I got this. Everybody have this? You can use the button run in order to get the Allan variance, Allan deviation, sorry. Okay, and to display the asymptote. What do you think of this fit?
Not so nice.
Not very nice. And why is it so bad? What will be the asymptote here? You see that we have something which is the red one on my plot is in tau minus 1. So it means that in variance it should be white phase. White phase or flicker phase. We don't know. But if you look carefully on the table, you will see that if you have flicker phase, it's not only a 1/2 square, there is also a log containing a tau. So it is the product of a log, and so it explains why it doesn't fit at all, because there is something which is not well fitted by a power law. So in my opinion, it seems that there is some some flicker phase noise in this. So what is this? And you know that Allan deviation is not at all the good one if you deal with this type of noise. What could be the good solution?
Modified one.
Sorry?
The modified.
The modified. This time is modified. Okay. So you have to. So we will try to. So I recommend to make a new panel, new time. Okay, I will load again the same file, VC0 new one. Okay, that's it. And I will remove, transform it in Y. Okay. And now I will select not a dev but M dev. M stands for modified. Okay. What do you think of this fit?
Very nice.
Very nice. Thank you very much. So clearly you see that it's very well fitted by an asymptote which is in tau minus 1. What is with modified Allan now? With modified Allan, which is the second column, what corresponds to 1 over tau square, because this is a deviation and the table is given in variance. And you see that it's really the flicker phase, which is here. So the main part of the noise is a flicker phase here. And you see that there are other noises. And I think that if you put the sum of these three asymptotes, which are very close together, you should retrieve a curve here which could fit approximately the data. So for me, the fit is quite good now. So what we could do now would be to verify if we look at the spectrum, if we retrieve something which is in F, but it's quite easy to do. I will make another panel. I will, as usual, use VCO here. Okay, and I will change okay, and I will ask him to compute the spectral density. And what you observe here in this area, what is the behavior of the spectral density? Sorry? What is the behavior of the spectral density in this part? The frequency is here, the spectral density here. The behavior is? I take, for instance, 1 decade here. When I take 1 decade here, it increased by 1 decade. It's F. The deviation. It's a linear. Yes, a linear value in F. So it means that we really have a flicker phase noise, which has a spectral density in F. You can even try to see if the value which is here correspond to what we obtain. In the 25 minutes that remain, I will try a little bit to show you how works the three-corner hat. So I didn't have time to explain what is the three-corner hat during my lecture, but I will try to go to give some clue right now. Imagine that you have a good clock and a bad clock. I have a clock which is here, which is a bad clock. I will put a bad clock with a square. How can I measure the stability of the bad clock? I will measure the bad clock against a good clock. So I will put here a time interval counter, and I will look at the difference between what. Consider that all the instabilities that we observe are due to the bad clock. The good clock is so good that it's not possible to see its instabilities. But what happens if you have two clocks? What can you do? You have two good clocks, for instance.
Then you need another bad clock or another clock to compute.
Yes, but it's the step beyond. But before, you can consider, at first step, you can consider that you have two clocks which are exactly the same stability. And when you obtain the Allan deviation, you can consider that half is due to the first clock and the other half is due to the other one. So you have to divide by square root of 2. But anyway, okay. But of course, if there is a clock which is very good in one part of the spectrum and another one which is very good in another part, it's not possible to know that. So in order to know exactly what happens, you need effectively, you can use a clock which is here, clock A, for instance, a clock B which is there, and clock C which is here, and you put three time interval counters between them. I will call it AB, for instance. This one is CA, and this one is BC. Okay. So what we will observe, we will have sigma square AB, sigma square BC, and sigma square CA. And what we can know is the fact that, for instance, sigma square AB is sigma square A plus sigma square B. And we consider that we have no correlation. It's very important. If you have correlation, it doesn't work. But plus the noise of the instrument I call BC, sigma square BC. Okay? You can do the same thing with the sigma square B plus sigma square C plus sigma square BC. AB, sorry, BC, and here sigma square C plus sigma square A plus sigma square CA. And you see that if I take, for instance, I will make the sum of these two ones, and I will make the difference with this one. Sigma square AB plus sigma square BC minus sigma square CA. What is? Imagine that you have. It was a device that I presented during my lecture yesterday. You have a device which will launch the counter when you have a rising edge from the one clock, and you will stop when you are rising edge of the other one. Mm-hmm. So you do that at each.
That's more or less different frequency counting.
Yes, yes. So in this case, you have directly the time error, time error, and if you do what we did with our data, you retrieve the frequency deviation from that. Mm-hmm. Okay. Okay. So if you do that, sigma square A plus sigma square B plus sigma square B plus sigma square C minus sigma square A minus sigma square C. So you retrieve here 2 sigma square B. We can imagine that this one will remove, and you have plus sigma square AB plus sigma square BC plus sigma square CA. We can imagine that we have sigma square AB equals sigma square BC equals sigma square CA because they are the same device. And in this case, we can consider that we have there is a minus sign here. I will call it sigma, and we got 2 sigma square B plus sigma AB, sigma BC plus 2 sigma square. Okay? So it means that in this case, you are able, if you neglect the noise of the counter, you are able to retrieve the Allan variance of the clock B in this case. And you can make another system in order to retrieve the variance of the clock A, the variance of the clock C. This is the so-called three-corner hat method. You see the three-corner hat is here. You can put that on your head if you want. Very beautiful. Okay, this is the first method which has been invented. I think it was, I don't remember, it was Dave Allan also, but I think he was included in the team who invented the three-corner hat. But a few years later, there was another invention which was not the variance, but the covariance. The equivalent of the covariance of Allan. You remember the difference between a variance and a covariance. A variance, for instance, if you have a quantity y, if you want to make the variance, you have the variance will be you take the square of the average of the square of y. Okay, but if you want to make the covariance of y1 and y2, the covariance will be of y1 and y2, you replace the square which is here by y1, y2. You can do exactly the same thing by using the covariance which have between these two AB and BC. Instead of doing what we did here, the variance of AB, you can make the product of YAB and YBC, and you will retrieve here the covariance of AB. It should be 1/2. You take back to the instead of doing the square of y1, y2 minus y1 square, you put covariance of AB BC. Sorry. You will have to do 1/2 YAB 2 minus YAB 1 multiplied by YBC 2 minus YBC 1. And we can demonstrate that if you do that, you will retrieve that this covariance, which will be exactly equal to minus sigma square B. So you will retrieve the variance of the clock B without to have the problem with this one, which retrieve also the variance of the device, which is here, the measuring device. So it's much better because you are not limited by the noise of the instrument device. It's possible with this witchcraft to go back directly to the variance of each clocks. Yes?
Which type of variance does it produce? Is it close to overlapping Allan deviation or modified Allan deviation?
You can do as you want. You can take. You just have to replace in the definition of the variance, which is here. Whatever the variance, you can use the Allan variance like that. It will be the Groslambert covariance, but you can use also the Hadamard. You change just what is inside. You change the square by a product between two, and it works for every variances.
Yes, yes.
And in this case, it's very useful because you can retrieve directly the variance of the noise, provided that you have uncorrelated clocks, and you have.
But noise are also uncorrelated.
Yes, and you should have data which have taken at exactly the same time. Perfect synchronization and uncorrelation. Sometimes it's very difficult to be sure that you have uncorrelated the clocks, but if they are correlated, you cannot go further, because if they are drifting all at the same time in the same manner, it's not possible to see it, of course. So this is the limit. This is exactly the counterpart of what is done in the spectral domain when you make a cross spectrum. That was explained by Enrico. Yes?
And what can we say about the system if in free corner cut the variance becomes negative?
Yes, sometimes the variance comes negative because, let's say, it's a little bit, it means that you are trying to estimate a very good clock with two bad clocks.
That's exactly happened, yes.
Yes, in this case, sometimes you retrieve a variance which is negative. What can we do with that? We put that to the garbage, but it means that you don't have enough information on this clock. Generally, what you obtain, if the clock is much better than the other one, you have an uncertainty domain which will be, which will have a maximum but no minimum. You are not able to see what is really the possibility of. You know that it's better than the bad clocks, in other words, but you don't know if it's real, if it's an infinitely accurate clock. It should be strange, but we don't know where is the limit in this case. We will very quickly see an illustration of that. I think perhaps I still have. So you see what I have to do. You see that in your playground directory you have three YKT data files, which are KNKAB, KNKBC, and KNKCA. It's exactly what I show you. KNK is the name of the measuring device, but anyway. So we will use that. You will enter in the command 3-corner hat, which is one of the program, one of the codes that is in SigmaTheta. You put these three ones, and you will put in the data file of the results with the .gcov, Groslambert covariance, it will put the result, and it will display at the screen also. So I will launch it. It's a little bit long because what is long is not the computation of the Allan, the Groslambert covariance. What is very long is the computation of the uncertainties, because the uncertainties, it's very important to get the uncertainties in order to have, for instance, if you have a value which is negative, for instance, but it's very important to get this negative value, the uncertainties, because it will tell you what is the PDF, the probability density function of the data, because it's no longer chi-squared. So it's much more difficult, much more complicated than this. So you see that he will change for each value. He will try to estimate for tau equal 1, tau equal 2, tau equal 4. He will give an error bars at each time. And after that, he will plot that. Yes?
And with this command, we are calculating 3-corner hat or the covariance?
It's covariance.
Because it's 3-corner in the name.
Yes, I call it 3-corner, but by default, it calculates the covariance. The result is quite the same. Not exactly, because there is you remove the noise of the measuring device. Mm-hmm. But if there is no noise, with the noise it's not possible to see it, you go through exactly the same result. Does it work?
For the movie.
Okay, that's it. So for the movie. So as I told you, here you have the measurement noise which decreases very quickly, so we don't really care. And what is interesting also is to see that sometimes one clock is better than the other one. After that, it's the worst. The green one, for instance, the green one is better for small time integration and so not so good for large integration time. And you see also that the red one is the best around 10 to the 4 seconds. So it means approximately 3 hours. But on one day, the better it seems to be the blue one. So in this case, you see that here, the red one, you are able to see what is instability. You have really a 95% uncertainty domain, which is between these two extremes here, whereas this was not possible to know the limit here. And so we can imagine that it's not very far from this limit here, from this value which is here. But now it's the blue one that you are not able to know its stability. So on the right-hand side of the graph, you always have very large uncertainty domain. Okay?